Hey guys, in this video we're going to talk about Chapter 16, Section 5, Integrals in Cylindrical and Spherical Coordinates. So cylindrical coordinates is very similar to polar. In fact, it's almost identical to polar with the exception that z stays as z in Cartesian. So in cylindrical, we can describe a point in space with just the radius, the same radius that we have in polar, theta, the same theta we have in polar, and z, just the regular z value in Cartesian coordinates. So we can see that, again, in polar, the theta and r were restricted to the xy plane, okay? And we can see that this point right here has an angle that goes out theta away from the x-axis. It has a radius, so the point goes out from the xy axis of r, and then it has some height of z. So we can describe any point in space this way. And just like in polar, x equals r cosine, y equals r sine, but we leave z fixed. And just like in polar, we have the identity x squared plus y squared equals r squared. So let's do some practice describing regions in cylindrical coordinates. So here we have apparently a wedge of cheese. Okay, that's what your textbook says this is. Wedge of blue cheese in particular. Yeah, so let's go ahead and describe this region in terms of r, theta, and z. Well, we can see where z varies pretty easily. Z is the height of a region, right? And so this region is going to vary from a height of 0 to a maximum height of 4 centimeters. So that's one component that we need. Z is between 0 and 4. And we can see that the radius, radius of this wedge of cheese, starting from the x-axis all the way out, or starting at the origin all the way out, is our radius. And we can see that our radius is 6 centimeters. Okay, that's how, that's the radius of the circle that the figure lies on. So r is going to be between 0 and 6. And theta, we can see from the picture that this maximum theta right here is pi over 6. So for this figure, we're going to have theta varying from 0 to pi over 6. And that's how we can describe this region in cylindrical coordinates. Okay. Now let's go ahead and use our identities to find the equation of the bottom half of a sphere in cylindrical coordinates. So we are interested in the bottom half of a sphere, so maybe something that looks like this. Okay, so there's the bottom half of our sphere, and it has a radius, right? It has a radius of 2. Okay. And it's centered at the origin. Okay, so let's go ahead and use our polar coordinates or our polar identities to figure out what this equation is in cylindrical coordinates. So again, we're just replacing x and y with our polar stuff, and we're leaving z as it is. So x in polar is r cosine theta, so I'm going to replace x squared with r cosine squared, plus y in polar is r sine theta, so I'll replace that there, plus z squared equals 4. Alright, so we have r squared cosine squared theta plus r squared sine squared theta plus z squared equals 4. If I factor out an r squared, I'm left with cosine squared plus sine squared plus z squared equals 4. And so by the Pythagorean identity, cosine squared plus sine squared equals 1. And if I subtract r squared from both sides, I get z squared equals 4 minus r squared. Then I can take the square root, and when I square root, I tack on a plus or minus sign. But in the context of this problem, it says, okay, z is going to be positive or negative, but this guy is always going to be negative. This guy is always going to fall because it's the bottom half of the sphere. It's always going to fall below the xy plane. And so we're going to choose the negative version here. So this is going to be negative root 4 minus r squared. So we want to find the equation for y equals root 3 times x in cylindrical coordinates. So we just want to change our x's and y's into r cosine and r sine. So y is r sine theta, and this is equal to root 3 times r cosine theta. Okay. So I want to simplify this as much as I can to figure out what this equation is. So what I'm going to do is I'm going to divide both sides by r, get rid of that, and then I have sine theta equals root 3 times cosine theta. Now what I can do from here is I can divide both sides by cosine to get sine theta over cosine theta is equal to root 3. Well, from trigonometry, sine theta over cosine theta is equal to tan theta. That's just an identity from trigonometry. So we have tan theta is equal to root 3. So what could theta possibly be? Well, tan theta is equal to root 3, and if we think back to trigonometry and our reference angles, the angle that has a tangent of square root of 3 is going to be pi over 3. Actually do this a little bit more like that. So this is pi over 3, and that's because pi over 3 has an x coordinate of 1 over 2 and a y coordinate of root 3 over 2. So when you do y over x, you get square root of 3, and that's precisely what tangent of theta is defined to be. Okay? So we know that pi over 3 will work here. Okay, so theta is equal to pi over 3. But tangent is also positive in quadrant 3. Okay, so tangent is also positive in quadrant 3 because both x and y are negative in quadrant 3. And this guy is going to be, well, let's see, this is pi over 3, this is 2 pi over 3, this is 4 pi over 3. So 4 pi over 3 has an x coordinate of negative 1/2 and a y coordinate of negative root 3 over 2. And so when you do y over x, just like we did up here, we are going to get that positive root 3 again. So if you want to write all possible thetas, what you could write is pi over 3 plus pi k, where k is an integer. That's going to cover all possible thetas that'll satisfy this equation because these guys are pi apart, right? If we do pi over 3 plus 1 pi k, we get 4 pi over 3. If we do pi over 3 plus 2 pi k, pi over 3 plus 2 pi, well then we're going to be back here and we're also going to get a tangent of root 3 from whatever angle that is. So this is just basic like trigonometry stuff. However, you know, if you come across a homework problem and your theta is restricted, say theta is between 0 and pi, Well, then we don't need to include any of this. All we would say is that theta is equal to pi over 3 because we're restricting where theta can be. It says theta is between 0 and pi, so we can have anything in the first or second quadrant. And the only angle in the first quadrant that satisfies that is pi over 3. There's no angle in the second quadrant that satisfies that because tangent is always negative in the second quadrant. So our answer here would be theta equals pi over 3 if we're restricting to this domain right here. Let's practice evaluating triple integrals in cylindrical coordinates over a region W. So they give us this function in Cartesian coordinates, x, y's, and z's, and they're telling us that the region W, so our limits of integration, we're going from r goes from 0 to 4, theta goes from pi over 4 to 3 pi over 4, and z goes from -1 to 1. And they tell us to use this integration order dr, d theta, dz. So let's go ahead and set up our integral and go ahead and evaluate this. So z is going to be last, so I'm going to put that on the outside from -1 to 1, right? I'm just looking at my integration order. Theta is in the middle, so theta varies from pi over 4 to 3 pi over 4. And the first one we're going to evaluate is with respect to r, so we're going from 0 to 4. And what I'm trying to integrate, well, this function, but I want to change x and y in terms of r cosine, r sine. So x is going to be r cosine theta, and we're squaring it just because of that there. Y is r sine theta, and we're squaring that as well. And unlike polar, we're just leaving z alone because we're working in cylindrical coordinates. And I'm going dr, d theta, dz. It's my order of integration. So let's go ahead and clean this up a little bit. Squaring these things, I get r squared. I get r squared cosine squared. Oh, I forgot my r up here. Oops. See how easy it is to forget? I forgot my r, dr, d theta, dz. Okay, so don't forget that r. That r is going to go there. Okay, so anyway, squaring this, I get r squared sine squared theta plus z squared. This is all times r, dr, d theta, dz. And we have our triple integral. Okay, simplifying this even further, what I can do is I can factor out an r squared on the inside to give me cosine squared plus sine squared, which I like. That's just 1. So I'm just cleaning this up before I actually evaluate my integrals. So this is equal to 1. That's nice. So I have this triple integral, and then I have r squared times 1 is just r squared, so hopefully I can just leave that as it is, plus z squared times r, dr, d theta, dz. Okay, so let's go ahead and distribute the r in there, and then I'll evaluate my triple integral. So let's see. Pi over 4 to 3 pi over 4, -1 to 1. Alright, so if I distribute that r in, I get r cubed plus rz squared, dr, d theta, dz. So I'm integrating with respect to my radius first, with respect to r first. So we're treating z like it's a constant here. And so let me do that integration. When I do that, I get r to the 4 over 4 plus r squared over 2, and that z squared is just being tacked on. And we're going from r equals 0 to r equals 4, right? So let's go ahead and plug in those bounds. So we get 4 to the 4th over 4 plus 4 squared over 2 z squared minus, and then when I plug in the 0 for r, that's all going to disappear, so I really just need this. Let's see. Alright, so this is, well, this is going to be, let me get my calculator. I feel like doing this by hand. So let's see. Okay, alright, so this is going to be, let's just clean it up a little bit. This is going to be 64 plus 8z squared. And so I integrate with respect to r, so let's go to theta next. We're going from pi over 4 to 3 pi over 4. And then we're going from -1 to 1 for z. Okay, so with respect to theta, basically, you know, these are just constants. So when we integrate with respect to theta, we get 64 theta plus 8z squared theta. We're going from pi over 4 to 3 pi over 4. Okay, so we have 64 times 3 pi over 4 plus 8z squared times 3 pi over 4. And then we're going to subtract off from that 64 times pi over 4 plus 8z squared times pi over 4. Okay, so let's go ahead and clean this up. Let's see. So I have 64. Well, how do I want to do this? I guess we can just clean it up as much as possible. Just simplify it. Okay, so this is going to give us 48 pi plus, let's see, 2 times 3 is 6, so this is 6 pi z squared minus 16 pi plus 2 pi z squared. Okay, and I've run out of room, so let's see. Alright, so we have 48 pi minus 16 pi. That's going to give us 32 pi. I'm going to actually rewrite this up here. So we have 32 pi. And then 6 pi z squared minus 2 pi z squared is going to be 4 pi z squared. And that's cleaned up. So now we're going to integrate this from -1 to 1 with respect to z. And I'm going to erase some of this stuff so we have some room here. Okay, so with respect to z, I'm going to get 32 pi z plus 4 pi z cubed over 3, and we're going from -1 to 1. So we have 32 pi times 1 plus 4 pi 1 cubed over 3, and then we're going to subtract off 32 pi times -1 plus 4 pi over 3 times -1 cubed. Okay, so let's clean this up. So we have 32 pi plus 4 pi over 3 minus, well, this is actually going to become a plus because that's negative inside. Negative times a negative is a positive, so this is plus 32 pi. This becomes a negative because it's cubed, so we have -4 pi over 3 times a negative is positive. Okay, so this is 64, let's write it up here, 64 pi plus 8 pi over 3. And let's see, common denominators, so 64 times 3 is 192 plus 8. Okay, so we get 200 pi over 3 is our answer here. Okay, so we want to write a triple integral in cylindrical coordinates giving the volume of a sphere of radius 3 centered at the origin. Use the order dz, dr, d theta. So when we're finding the volume with triple integrals, we are integrating z equals 1, and the bounds of our integral is going to be the region that we're trying to find the volume of. So all we need to do is describe the region of the sphere centered at the origin. So that's what our main task is going to be, so that we can integrate this guy and figure out what the volume is. So we have the sphere centered at the origin of radius 3, so r is going to equal 3. And we need to figure out how to bound this. So how can we describe this region in cylindrical coordinates? Well, your r, if you imagine, you know, this sphere right here, the maximum radius that this region could have, any member of the set can have, is a radius of 3, and the minimum value is a radius of 0. So this radius is going to range from 0 to 3. Now theta, again, you know, this is, you can imagine theta is just on your xy plane, and so what is theta sweeping out? Well, if you were to move this line and sort of sweep out this region, you're going to see that theta is going to be 2 pi, right? We can make a full circle to sweep out this region. So theta is going to vary between 0 and 2 pi. And z, our height, is going to depend on a given radius, right? So a point in our set, the set being the sphere, its height is going to depend on the radius. So z is going to be between something and something, but it's going to depend on what the radius is. So what we can start to do to figure this out is we can just write the equation of the sphere centered at the origin with radius 3. That equation is going to be x squared plus y squared plus z squared equals 3 squared, which is 9. So this is just the equation of a sphere centered at the origin with a radius of 3. And what I can do, I want z in terms of r, right? Because z is depending on r. What I can do is I can sub in r squared for x squared plus y squared, just using that idea from polar. And I get this. And then if I isolate z, I get z squared equals 9 minus r squared. If I take the square root, I get z equals plus or minus square root of 9 minus r squared. So my lower bound is the bottom half of the sphere, which is negative root 9 minus r squared. My upper bound is the top half, which is going to be the square root of 9 minus r squared. Alright, so using these bounds, it doesn't say to evaluate the integral, but I'm going to do it anyway, just so we can have some practice doing this. So we want to use the order of integration dz, dr, d theta. So we have our triple integral, and our theta is going to be the last thing we integrate with respect to. So I'll put that on the outside. We're going from 0 to 2 pi. On the inside, in the middle, we have r. R is ranging from 0 to 3, and our z is ranging from negative square root of 9 minus r squared to positive square root of 9 minus r squared. And again, with these volume problems, we're integrating 1. Okay, so so because we are integrating in cylindrical coordinates, we don't want to forget about that r dr d theta idea. So r is going to be there, but we want to make sure the dz comes first, followed by the dr, followed by the d theta. But again, you can't forget that r, just like with polar coordinates. So let's go ahead and integrate this with respect to z first. So with respect to z, this is just zr, and we're varying between negative root 9 minus r squared to positive 9 minus r squared. Again, this is z equals. So if I evaluate at my bounds here, I get square root of 9 minus r squared times r minus, and then this is going to be minus r root 9 minus r squared. Alright, so this is going to give me 2r square root 9 minus r squared when I simplify that. Okay, so I've integrated with respect to z. Now I need to integrate this thing with respect to r. So let's go ahead and do that. So now I'm just left with the double integral. So I'm going from 0 to 3 dr d theta. Alright, so this is kind of a complicated integral. So what I'm recognizing here is that under the radical, if I take the derivative of that, I'm going to get negative 2r, and so I have some sort of cancellation that's going to happen if I use a u substitution. So that's the strategy I'm going to use here. I'm going to let u equal 9 minus r squared, and therefore du is going to be negative 2r dr, and therefore dr is going to be du over negative 2u. So I'm going to make those substitutions. I'm going to forget about the outside integral for now, keeping in mind that here my integral, I'm going from r equals 0 to r equals 3, and I have let's see, yeah, so I have 2r square root of u, and instead of dr I have du over negative 2u. Wait, that's not right. I meant negative 2r. Let's change that up there. Negative 2r. There we go. Okay, cool. So these are going to cancel, and that's what we wanted. So I'll bring that negative to the front, and I'm going from r equals 0 to r equals 3. Okay, so I want to be careful here because my bounds are in terms of r, but when I integrate, I want this to be in terms of u, so I need to change my bounds, okay? So instead of r equals 3 and r equals 0, I need to go up here, and I need to say, okay, well, I need to change these bounds in terms of u. So I know that u is equal to 9 minus r squared. So instead of r equals 0, well, if I plug in 0 in for r, I get 9 minus 0 squared. Instead of r equals 0, this actually becomes u equals 9. Alright, so let's change that because I'm integrating with respect to u. So this is going to be u equals 9. And likewise up here, when r equals 3, I want to change that in terms of u. So instead of r equals 3, well, u equals 9 minus 3 squared. That becomes u equals 0. So these are my new bounds here that I'm going to use. Alright, so let's go ahead and integrate this thing now. So this is just u to the 1/2. We're going from u equals 9 to u equals 0. And if I add 1 and divide by that, I'm going to get, let's see, I'm going to get u to 3/2 over 3/2, which is just times 2/3. And that negative can just hang out on the outside for now. And I'm going from u equals 9 to u equals 0. Okay, so u equals 0 comes first, so I have negative 2/3, 0 to the 3/2 minus 2/3, 9 to the 3/2. Okay, so when that is all said and done, those negatives are eventually going to cancel out and make a positive, so that becomes 0 right here. And let's see what this becomes. This is Square root of 9 cubed, so it's 3 cubed is 27, divided by 3 is 9. 9 times 2 is 18. So these double negatives, this becomes a positive 18. Okay, so I integrate with respect to r, so let's go ahead and do our last thing, which is respect to theta. So I'm going from 0 to 2 pi, and this is d theta. So this is pretty straightforward. With respect to theta, this just becomes 18 theta, and I'm going from 0 to 2 pi. And yeah, so if I plug in 2 pi, I'm going to get 36 pi minus 0, so this is our answer here. This is the volume of that sphere. And we can check this answer is correct with our formula from geometry. So from geometry, or from Google, or from wherever you see this, the volume of a sphere is going to be equal to 4/3 its radius cubed. Okay? Now what was the radius of our sphere? The radius of our sphere was 3. Okay, so the volume of the sphere, oh, and I forgot the pi. Always forget the pi. 4/3 r cubed pi. Anyway, the radius of the sphere is 3, so this is going to give us 4/3, 3 cubed times pi. So that's 27 over 3 is 9, right? And 9 times 4 is 36. 36 times pi is 36, so that checks out. So that is how you can find the volume of a sphere using calculus. Alright, so we want to write a triple integral that gives a volume between the cone z equals square root of x squared plus y squared, the first quadrant of the xy plane with x squared plus y squared is less than or equal to 21. Okay, so we need to find our bounds for r, theta, and z. Okay, so r is between what and what, theta is between what and what, and z is between what and what. Well, they tell us that we're only interested, so theta depends on the xy plane, right? And they tell us that we're only interested in the first quadrant of the xy plane. So if we were to draw that out, first quadrant's right here. This is the xy plane. And so theta is going to vary in this first quadrant from theta equals 0 to theta equals pi over 2. This could be theta. So our theta is going to vary between 0 and pi over 2. We know that for sure. Now, where are r and z going to vary? Well, since we're concerned with the xy plane, so the z is bounded by the cone and the xy plane, well, we know that the lower bound for z is going to be 0, because on the xy plane, z is equal to 0. Now, the upper bound for z is going to depend on r. And if we look at this equation right here, z is equal to square root of x squared plus y squared, well, we know to change x squared plus y squared in a polar, that's just r squared. So z is equal to the square root of r squared, and therefore the upper bound is going to be z equals r. So this is describing that cone in terms of polar. All right, so z is going to be between 0 and r. And r we can get from this clue. So it says that x squared plus y squared is less than or equal to 21. Well, we know that x squared plus y squared is equal to r squared. So therefore, r squared is less than or equal to 21. Taking the square root, r is going to be less than or equal to root 21. And therefore, r is going to vary between 0 and root 21. Alright, so now that was it. That's the hard part. Now we just need to set up the integral. And for this one, I'm not going to evaluate it just because, you know, we've done a lot of these already. But the hardest part is to just set them up. So let's go ahead and set these things up, and I can choose the order of integration. Typically with these cylindrical problems, I'm going to choose dz first. So for volume, we have 1. And then, of course, because of the polar integration, we're going to do r. And I'm going to do dz. I'm going to do z first, followed by r, followed by theta in cylindrical coordinates, okay? So since z is coming first, I'm going from 0 to r. Next comes r, that's from 0 to root 21. And finally, theta is varying from 0 to pi over 2. So that should give you the volume of that region that's described. Alright, so let's try this one. We want to write a triple integral that gives a volume of the cap of the solid sphere cut by the plane z equals 2. Alright, so we want to know, what the volume of this cap is right here, of the sphere. And this sphere is cut by the plane z equals 2. Okay, so this is our plane z equals 2. Not a great picture, but that's where it's cut. So we need to find our bounds for z, r, and theta. Okay, so we can see that, that theta, this cap, theta is going to vary in a circle, right? So theta is going to go all the way around and sweep out a circle. So theta here is varying between 0 and 2 pi, for sure. And they give us this equation up here. They say, okay, well, x squared plus y squared plus z squared is going to be less than or equal to 53. Okay, so what I can gather from that, x squared plus y squared is the same thing as r squared. So I get r squared plus z squared is less than or equal to 53. And if I isolate z squared, I get z squared is less than or equal to 53 minus r squared. Taking the square root, I get z is less than or equal to positive square root of 53 minus r squared, because we're concerned with the top half of the sphere, so we're not going to take the negative square root here. All right, so this is the upper bound. It says z is less than or equal to that, and the lower bound is going to be z equals 2. That's that plane right here. So the minimum height is z equals 2. The maximum height is root 53 minus r squared. So let's write that for z. So z is going to be greater than or equal to 2 and less than or equal to square root of 53 minus r squared. All right. So now what about my radius? What about my radius? Well, I'm going to get the radius if I just plug in z equals 2 in here. Well, then I'm going to get an expression for the radius, because I know that x squared plus y squared is equal to r squared. And so what I have here, I have r squared plus z squared is less than or equal to 53. So we have r squared plus z squared is less than or equal to 53. And I want to figure out what the radius is. Okay, where is the radius going to vary? Well, where the radius is going to vary is going to depend on z equals 2, right? That's going to give me my radius. So if I plug in z equals 2, I get r squared plus 2 squared less than or equal to 53. And I'm getting r squared is less than or equal to, let's see, if I, that's going to be 53 minus 4 is 49. Take the square root, and I get r is less than or equal to 7. Okay, so that's my radius bound. So my radius is varying from 0 to 7. And that's really all I needed to know here. So now I can write the triple integral. And if I want to, I can evaluate it. I'm not going to do that here, though, just because we've already done so many examples where we evaluate integrals. But yeah, so I'm going from z equals 2 to square root of 53 minus r squared. 1 r dz, dr, d theta. It's the order that I'm using. So that was z. So next comes r. So r varies between 0 and 7. And then finally theta is going to vary between 0 and 2 pi. Okay, so that's my integral to find the volume of that cap. So the final coordinate system that we're going to talk about is the spherical coordinate system. And this coordinate system is useful when your region of integration is spherical. It can make your life a lot easier if you have a super complicated integral. Spherical coordinates can help. So we talked about three different, well, really, yeah, so we talked about rectangular. To just describe a point in space, we can use rectangular, x, y, and z. We can use cylindrical. We can describe a point by r, theta, and z. And finally, we're going to talk about spherical. So we can describe a point in 3 dimensions with 3 things. The first thing is rho. Okay, this is the Greek letter rho. It kind of looks like a lowercase p. We can describe both rho, this angle phi, and an angle theta. Okay, theta is going to be the same as it was in polar coordinates. So what is rho? Well, rho is just going to be the distance from a point in space to the origin. Okay, just the classic distance formula that we talked about in the very beginning of the course. That's what rho is defined to be. Phi is defined to be the angle between the positive z-axis and the line through the origin and the point P. And theta is the same as in cylindrical coordinates. So here we have a representation of a point P in rectangular XYZ, and it's saying that, you know, it's telling you what all of these values that I just mentioned were. Rho is the distance from the origin to P. Theta is just the same as in polar coordinates. It's that it's made with the x-axis and the radius. And phi is going to be an angle made with the positive z-axis and that rho going out to your point xyz. All right, so that's how we can describe a point in spherical coordinates. All right, so what's the relationship between rectangular / Cartesian and spherical coordinates? Well, we're going to let rho vary from 0 to infinity since rho is a distance. Phi is going to vary between 0 and pi, and we're going to see why we're making those restrictions on the last problem on our slides here. And theta is going to vary between 0 and 2 pi. And I'm not going to really go into detail why these identities work, just because, you know, it might not be necessary. If you want to explore the relationship between the Cartesian and spherical coordinates, like derive these formulas, you should, you know, if you're interested in that. But I'm just going to give them to you for now, these identities. It says when computing integrals in spherical coordinates, we're going to have dv equal to rho squared sine phi d rho d phi d theta. So just like in polar when we had r dr d theta, this is the stuff that comes along with whatever we're integrating. And we have these identities to use here. So let's go ahead and use these identities to write an equation for the plane z equals 2 in spherical coordinates. Okay, so we want to change z into spherical coordinates, and we have this identity right here that z is equal to rho cosine phi. So z is equal to rho cosine phi. That's our identity here. And so z equals 2, so we have 2 equals rho cosine phi. And if we want to isolate rho, by dividing both sides by cosine of phi, we could do that. So rho is equal to 2 over cosine phi. So this would be an equation in just spherical coordinates. So spherical coordinates only involve rho, phi, and theta. Okay. So write an equation for x plus y equals 4 in spherical coordinates, and we're going to isolate rho. Okay, so we want to get rid of the x and the y, and again we go back to our identities here. X is rho sine phi cosine theta, and y is rho sine phi sine theta. Oh, I think I got that backwards. So this is sine phi cosine theta. Alright, so those are my identities here, and again, I'm just using these identities right here. Okay, so now all I have to do is sub these in. So x is rho sine phi cosine theta, and we're going to add y, which is rho sine phi sine theta, and this equals 4. Okay, so I want to isolate rho, so I'm going to go ahead and factor out a rho so that I can do that isolation. And when I factor out a rho, I get sine phi cosine theta plus sine phi sine theta is equal to 4. So I'll go ahead and divide both sides by all of this to isolate rho. Okay, so there's my equation with rho isolated. Notice I don't have any x's and y's, I just have phis and thetas. Okay, so we want to evaluate the triple integral in spherical coordinates of the function 2 cosine phi. And our region that we're considering theta varying between 0 and pi, phi varying between 0 and pi over 4, and rho varying from 3 to 4, and we're going to use d rho, d phi, d theta as the order of integration. Alright, so let's go ahead and write this out. Okay, so just based on our order of integration, theta is the outermost integral, so we're going from 0 to pi. Our middle is phi, so that's 0 to pi over 4, and our rho is going from 3 to 4. Alright, and we're integrating 2 cosine phi, and what we're going to tack on, just like with polar coordinates here, remember this is where I'm getting this, is right here. We're going to tack on this rho squared sine phi. Okay, so I want to make sure I tack on the rho squared sine phi, and my order is d rho, d phi, d theta. Okay, so before I even start anything, I'm gonna try to clean this up beforehand so that when I integrate it's not as messy. And what I notice here is this 2 cosine phi and the sine phi is, part of a double angle identity. So the double angle identity from trig tells us that the sine of 2 times an angle, in this case it's phi, is equal to 2 times the cosine of phi times the sine of phi. Okay, so that's just a double angle identity. So I'm going to replace what I have underlined in yellow with sine of 2 phi. That's what I'm going to do first to make this as clean as possible. Okay, so I'm going to replace that with sine of 2 phi right off the bat before I even do any kind of integration. And now I'm going to integrate with respect to rho first. Okay, so everything else is a constant except for rho. So when I integrate this with respect to rho, I'm going rho cubed over 3, and my bounds for rho are 3 to 4. So I'm going from, and I need to tack on that sine of 2 phi. So I'm going from rho equals 3 to rho equals 4. So I have 4 cubed over 3 sine of 2 phi minus rho cubed over 3 sine of 2 phi. Okay? Alright, so let me go ahead and simplify this. Okay, so I'm getting 37 over 3. So this is going to be 37 over 3 sine 2 phi. And now let's take care of this integral with respect to phi. So I have d phi and then d thetas on the outside. Okay, so with phi, I'm going from 0 to pi over 4. And then finally with theta, I'm going from 0 to pi. Okay, so let's go ahead and integrate this with respect to phi. So I'm just going to bring this integral down here and just leave the 0 to pi alone for a second. I'm going to pull out the 37 over 3, and now I have sine of 2 phi, d phi. Okay, so what I'm going to do here is the classic little u substitution trick. So I'm going to say, well, we're going to let u equals 2 phi, and therefore du is equal to 2 d phi, and therefore d phi, if I divide both sides by 2, is du over 2. Alright, so making those substitutions and just keeping in mind my bounds here, originally I'm going from phi is equal to 0 to phi is equal to pi over 4. I want to make sure I change that because now I'm integrating with respect to u. And so when I plug in d phi, that's du over 2. So I'm going to pull out the 1 over 2 to the front here and make that 37 over 6 when I pull out that 1 over 2. So the last thing to change are these limits here. Okay, so instead of phi, we want to be in terms of u. So u is equal to 2 phi. And so if I plug in 0 here, well, I still get u equals 0, so that's fine. That can stay as it is. When I plug in pi over 4 in for phi, I get 2 times pi over 4 for u, which becomes u equals pi over 2. So instead of phi equals pi over 4, this is going to be u equals pi over 2. And let's go ahead and integrate with respect to u at this point. Alright, so this is going to become negative cosine of u. We're going from u equals 0 to u equals pi over 2. And so I'm going to go ahead and plug in my bounds up here. I still have the 37 over 6 just kind of chilling on the outside. And then I have negative cosine pi over 2 minus negative cosine of 0. And I'm going to erase some of this stuff so I have more room. Running out of room here. Okay, so this is going to give me 37 over 6. Negative cosine, well, cosine pi over 2 is 0, so this becomes 0 plus cosine 0. And cosine 0 is 1. So I just get 37 over 6 when I do this. Alright, one more to evaluate. So we just did with respect to phi. Now let's do with respect to theta, and I'm going from 0 to pi. So we're going from 0 to pi. We're doing 37 over 6 d theta. Okay? So let's go ahead and integrate this. So that just becomes 37 over 6 theta. And we're going from 0 to pi. So our answer here, if I plug in pi for theta, I'm just going to get 37 pi over 6. And that is my answer.